Now that you've covered the concepts of position and velocity and acceleration, now we're ready to move on to the concept of forces. Now, forces is one of the most fundamental concepts in all of physics. In almost every problem, you'll start by looking at the problem and describing what forces are acting on an object. Now, before we can go any farther, we should look at what is a force. Simply put, a force is anything that causes something to accelerate, to change its speed. So now, this seems a little counterintuitive at first. What happens if you try to push on a school bus or on the side of a building? Clearly, you're exerting a force. You're pushing really hard. But it isn't accelerating. The velocity isn't changing. I guess unless you're super strong. So we need to have a slightly better definition, it seems. And in this case, they're not moving because there's another force pushing back. The friction on the wheels of the school bus stops it from speeding up. And all the forces that hold together the walls of the building stop it from being pushed over. So instead we say, a force is something that causes an object to accelerate if no other forces are acting on it. So if it weren't for friction, if you were on a really smooth ice skating rink or in outer space, for example, you could push on a school bus and cause it to accelerate. It might only accelerate a little bit, but it would accelerate some. Now that we've covered the concept of what a force is, we should now look at what the units of forces are. And in the SI system, a force is measured in newtons, named after Isaac Newton, the person who invented most of the physics that we use today. I seem to have misspelled his name there. And if you remember, a couple lectures ago, I described that the basic units for SI that we're using are kilogram, second, and meter. And in this case, 1 newton equals 1 kilogram meter per second squared. And don't worry if you don't know what that means. We'll in a later lecture be going over why that's the case. But just for now, know that you can multiply and divide by seconds and kilograms and meters, just like you would any other unit. And in the English system, it's a different unit. Interestingly enough, it's actually the unit of the pound, or lb for short. And while it seemed like the pound is a measure of weight, not of force, what we actually find out is when we say weight, we mean force exerted by gravity. So we can actually convert from pounds to newtons, and 1 pound equals 4.4 newtons. So in a physics concept, the pound is actually not the measure of mass, but of force instead. Now so far, we've talked about forces in terms of the acceleration they've produced. And if you remember from a couple lectures ago, acceleration is actually a vector concept. It needs both a magnitude and a direction. And if you ever have trouble remembering this, you can go back and watch the animated movie Despicable Me, where there's a very funny supervillain who claims that he commits crimes of both magnitude and direction. So he names himself Vector. And what this means is it's not enough to just say how much a force is. 10 newtons of force doesn't tell you everything about the force. You also have to say what direction it's in. And you can do this a number of ways. You can say, is it north, is it south, east, west, up, down? You can define a coordinate system and say x, y, z. You can say it's a number of angles separated from this. And next lecture we'll go over all of these different ways and talk about the advantages and disadvantages of both. But for now, just know, force is a vector, so you can express it as an arrow. So we'll point you down, we're pointing one called the force of gravity. So now let's say we want to take a rock. We want to look at all the forces that are acting on it. Since forces are vectors, we can draw all of the forces as arrows. So we have our rock here, and it's sitting on the ground. And the force of gravity is pulling down on it. And since the force of gravity is pulling down, but it's not falling down, there must be some other force counteracting this pull. And there is. This push, we call it the normal force, or F sub n for short. And it just means the ground pushing up on the rock so that it doesn't fall down due to gravity. And if you've ever stood up for a long amount of time and your feet hurt, it's because your shoes are pushing up on your feet and holding you up. And in a free body diagram, you draw all the forces acting on it. So now let's say a guy comes up, and he starts pushing on the rock. We then need to say there's like the force of the push going in this direction. And then in the opposite direction, there's the force of friction, or F with a little f underneath it. So now that we've drawn all of the different forces on this rock, now we can see exactly how it's going to behave depending on these different forces. And next lecture we'll talk about how these forces cancel out and what the best way to add and subtract forces is.